We're going to continue 5.4 here with being able to take the derivative of exponential functions. Okay, so theorem 5.11 or 511 here. If we take the derivative of e to the x, we get e to the x. It's probably one of the easiest derivatives you will ever have to take as we kind of move on through getting through advanced topics. The derivative of e to the x is e to the x. Now, obviously, we're going to use case number 2 more often than not. The derivative of e to the u is e to the u times du dx. So really, essentially, your derivative is always going to be e to whatever that exponent is times the derivative of what the exponent is. Okay? So let's go through example 7. We're going to take the derivative of e to the 2x minus 1. So for simplicity purposes, we can use U-Substitution to start, but as we work through this, I think you'll see that you may not use it. But let's let u equal 2x minus 1. Therefore, our du is 2 dx. So, following the rule up there, the derivative, we're going to rewrite that as e to the u because we did U-Substitution. And so when we take the derivative of e to the u, it ends up being e to the u times du. Okay? So, we end up getting e to the 2x minus 1 times 2, and then we rewrite it, so it's 2e to the 2x minus 1. Let's look at example 8. We have the derivative with respect to x of e to the negative 3 over x. For simplicity, we'll use U-Substitution again. U is going to be negative 3 over x. Du is 3 over x squared. So now we know how to take the derivative of e to the u. We rewrite that as e to the u. The derivative of e to the u is e to the u times du. So it's e to that stuff, e to the minus 3 over x, times the derivative of that stuff, which is 3 over x squared. So our final solution is 3e to the minus 3 over x divided by x squared. I think you'll find these to be relatively easy here. Example 9, where we have the function e to the 2x. Okay, I'm going to do this without U-Substitution. U-Substitution still works, but I kind of want you to start being able to do these in your head. The derivative of e to the 2x is e to the 2x times 2. 2 being the derivative of the 2x portion. Alright, and we know that the derivative of e to anything is going to be e to the anything times the derivative of whatever that exponent is. So our final solution is 2e to the 2x. Let's look at example 10 here. Trying to pick off ones that are very similar to your homework problems so you can kind of follow right along. We're going to find the derivative of y equals e to the square root of x. Okay, so best bet for us, we know we're going to take the derivative of e to the square root of x. We know the first part of the answer is e to the square root of x times we have to take the derivative of the square root of x, which ends up being 1 over 2 square roots of x. We've done that in past chapters, so that one should be pretty easy. I'm not going to go step by step there, but we should all know how to do the derivative of x squared. So our final solution is e to the square root of x divided by 2 times the square root of x. Another one very similar to your homework problem. You need to start recognizing things like product rule, quotient rule, and chain rule when you see these. If you get past that and recognize that right away, we'll be good. Notice there's two functions multiplying each other. We have x cubed times e to the x. So that automatically tells me I got to use the product rule because I have two functions times each other. I have an f of x and a g of x. So remember, the product rule is first times the derivative of the second plus the second times the derivative of the first. Or I should say the first term times the derivative of the second term plus the second term times the derivative of the first term. That's better nomenclature there. So we take x cubed, that's the first term, times the derivative of e to the x, which is e to the x, plus we take the second term, which is e to the x, times the derivative of the first term. The first term is x cubed, its derivative is 3x squared. So when we work through all this, we end up with x cubed e to the x plus 3x squared e to the x, or we can factor out e to the x and be left with x cubed plus 3x squared. Just kind of depends on your homework. It's multiple choice, so you might have to sometimes tweak your answer at the end or simplify a little bit more, or factor or distribute to get the correct answer. Alright, we're going to look at example 12 first. We want to find the derivative of y equals e to the negative x squared. So First steps first, right? We get to take the derivative of this, we get e to the minus x squared times the derivative of negative x squared, which is negative 2x. So final solution is negative 2x, e to the negative 2x, or e to the negative x squared. So let me rephrase that. Y prime is negative 2x e to the minus x squared. Alright, let's move on to example 13. We want to find the derivative of y equals e to the 3x to the 4th power. So, following suit, y prime is the derivative of e to the 3x to the 4th is e to the 3x to the 4th times the derivative of 3x to the 4th, which is 12x cubed. So our final answer for y prime is 12x cubed, e 3x to the 4th. So, here we're combining all kinds of good worlds now. We want to find the derivative of y equals the natural log of 1 plus e to the x divided by 1 minus e to the x. First thing I always look for with natural logs is being able to rewrite them. So we spent a lot of time in 5.1 rewriting natural logs. So we should see that that's a quotient. We rewrite it as subtraction. So y equals natural log of 1 plus e to the x minus natural log of 1 minus e to the x. Now we take the derivative of each one. Remember, the derivative of like natural log is 1 over that stuff times the derivative of that stuff. Okay? I know that's real technical jargon there, but it's 1 over e to the x, or I'm sorry, in this case the natural log of 1 plus e to the x, its derivative is 1 divided by 1 plus e to the x times the derivative of 1 plus e to the x is just e to the x. On the right hand side we have minus natural log of 1 minus e to the x. Its derivative is 1 over 1 minus e to the x times negative e to the x. So that negative and that negative makes a positive. So our final answer, before we simplify and try and combine, is e to the x over 1 plus e to the x plus e to the x over 1 minus e to the x. Sometimes we got to simplify and combine, so our best bet, we have to find a common denominator. The common denominator in this case is actually just multiplying both denominators, so our common denominator should be 1 plus e to the x times 1 minus e to the x. So the left hand side of that equation piece there, on the left side we're missing the 1 minus e to the x, so we have to multiply it by 1 in the form of 1 minus e to the x over 1 minus e to the x. And on the right hand side it's missing the 1 plus e to the x. We're going to multiply it by 1 in the form of 1 plus e to the x divided by 1 plus e to the x. So on the bottom we have a common denominator of 1 minus e to the x times 1 plus e to the x. On top we're going to distribute that e to the x through on the left hand piece, and there's one on the right hand piece. So when we do that we get e to the x minus e to the 2x. Remember, when we multiply terms with a common base, we add the exponent. That's why it's e to the 2x. Plus e to the x plus e to the 2x. The e to the 2x's cancel because one's positive and one's negative. So we're left with e to the x plus e to the x, which gives us 2e to the x. And on the bottom we actually FOIL all that out. It's a difference of 2 squares essentially, even though e to the x isn't a square, but the middle terms fall out, so we end up with 1 minus e to the 2x in the denominator. Okay, remember, multiplying two things with a common base, we add the exponents. That one's very similar to a homework problem that you have as well. Okay, this same principle as the last one, just without the natural log. Okay, so we're not going to rewrite that as a minus. You need to recognize that this is a quotient rule. Okay, so remember, the quotient rule is low d high minus high d low all over low low, if we kind of remember that little jargon. So it's low e to the x minus 1 times the derivative of the high, which is just e to the x, minus the high term, which is e to the x plus 1 times the derivative of the low is just e to the x. Remember, the ones, both derivatives are 0. All over low low, so we have to take e to the x minus 1 and square it. So on top we're going to distribute through e to the x on the left portion and on the right portion. When we do that, it works out similar to what we did in the last problem. We get e to the 2x minus e to the x minus 2x, e to the 2x minus e to the x. The 2x, the e to the 2x's fall out, and we end up with negative 2e to the x divided by e to the x minus 1 quantity squared. So we just combined like terms right there. No need to expand out the bottom. There's nothing that nicely cancels out and does anything with that for us. Alright, let's look at example 16. We're going to find the derivative of y equals 5e to the x sine of x. We need to once again recognize we got to use a product rule here. There are two functions multiplied by each other. The first g of x is 5e to the x, and our f of x is sine of x. So remember, product rule is first times the derivative of the second plus second times the derivative of the first. So our first term is 5e to the x, our second term is sine of x. So first, 5e to the x times the derivative of the second, derivative of sine is cosine, plus the second term, which is sine of x, times the derivative of the first term is just 5e to the x. Since there's nothing else in that exponent other than the x, it's just really just multiplied by 1. Common factor we can pull out here is 5e to the x, so when we rewrite that, it's 5e to the x times cosine of x plus sine of x. That is not a Pythagorean rule. Those are not squared. That's as simple as this gets. So that ends taking the derivatives of exponential functions. In the next video, I'm going to discuss integrating exponential functions, starting off with theorem 5.12.